if I'm considering the top of the ride, a person sitting there, they're traveling in a circular path. Is there any doubt about that? Now, in order for them to travel in a circular path, the unbalanced force must be directed towards the center of rotation. I'm keeping that in mind when we're looking at somebody at the top. That means the direction of the net force has to be downwards. That's the center of the path they're traveling on. So when I consider the forces acting on them, no, there's only two mg downwards and normal force from the chair upwards. Any question about that? Now, we'll work just this one to the end, because once you've worked this one, probably working the one at the bottom will be about the same. Now, this is a Newton's second law problem, but they're traveling in a circle. I have not veered away from this yet, have I? Any question? All I did is I put a C there after the A. Now, I've told you to direct the positive direction in the same direction as the acceleration. So I'm going to make downwards positive, which makes mg minus normal force equal to mv squared over r. Any question about any of these choices? Well, we need something for v. And you may or may not know how to handle this. We talked briefly about it yesterday, not in any great depth. But I also know that you guys are not naive. You know things. You know that making one rotation means that you're traveling one circumference. Right? That's a rotation. And that means one circumference in 6 seconds. So now I have meters per second. Right? I know I expect a lot out of you guys, but this isn't a lot. But that's why today's not the quiz. Now, I'm going to make a small aside here. And this is just for all the people who really need this. And it's probably about 3/4. So it suggests that there might be more than one way to write the centripetal acceleration. V squared over r is one of them, sure. But also, I could put it in terms of the angular speed. You guys see what I'm saying? So a little bit of work there tells me that centripetal acceleration can be written as omega squared times r, or v squared divided by r. These are both legitimate ways of dealing with the centripetal acceleration. All right. A lot there, so I'm going to get all that out of the way. And because I like to use my new stuff, like getting new toys at Christmas, I have a new equation. I'm so excited. Omega squared r. Okay. All right. That really is it. That's this problem, isn't it? Solve this for normal. Get my mg minus m omega squared r. And now you're just plugging in numbers and getting answers. That part's the least interesting thing to me. Now, I could put the numbers in if you're desperate for what the numerical answer is. But can we just recognize that the guy at the bottom is going to have a slight variation on this? the weight is the same, but the normal force has to be greater because the unbalanced force has to be towards the center, and that's upwards now. So I expect to feel heavier at the bottom and lighter at the top. Moreover, and this part's not terrible, but keep it in mind, this is normal minus mg, because I'm going to change my direction of positive to be upwards to match the direction of the unbalanced force. And that's going to equal m omega squared r. So that the normal here is the sum of these two things. Now, I've tried to do this in every class when I teach stuff like this, and I've tried to make it a big deal, and some people pay attention to this and some people don't. And I'm a little frustrated because I don't think I have everybody's attention earlier today, so I'm really hoping that you'll notice that a negative sign is rearing its head here. Negative signs represent things you should be careful about. Plus signs are no big deal, right? As long as the Ferris wheel can hold together and provide that normal force, you can spin that sucker as fast as you want until the person vomits or becomes a puddle of goo because there's so much normal force that it just squishes them down to nothing. That's not true here. There seems to be the possibility where I can get a 0 for my answer. And normal forces can't pull down. So once that normal force goes to 0, I'm representing a speed at which they are no longer connected to the Ferris wheel. Right? Seems to me like I have an inflection point. I have a maximum velocity for the Ferris wheel that will keep the people from being flung off the Ferris wheel. Because if I go faster, their horizontal velocity now will be faster than what is necessary to travel in a circle, and they will become a projectile and have a parabolic path and not a circular path. So we want to stay beneath that. These kinds of threshold problems are, these are the problems I like, and they're definitely problems that AP likes. All right. All the same ground in all of the classes. That means covering, or at least talking about, the record player problem. As if you guys know what a record player is. Well, some of you might. And I'm not trying to see which one of you is so hip that you listen to records. Because they're never going to say the word record on the AP exam. They're going to say spinning disc because they want to make sure they can get everybody's attention here. So spinning disc, and it's either the bug crawling on the disc or a coin on the disc. It doesn't really matter which one it is. Let's go coin on the disc. And the disc is spinning this way at some rotational speed omega. And let's say that the coin is some distance r away from the edge. The problem is either what is the minimum coefficient of friction for the coin to stay on the record, or what is the maximum speed of the record to keep the coin from flying off. It's some version of that. And to understand this problem is to understand that we are looking top down on the record right now. And one of the things I talked about yesterday is emphasizing the correct point of view to identify all of your forces. I don't think this is the correct point of view to emphasize all my forces. Because I'm pretty sure the frictional force is going to have to be this way. That's where the unbalanced force has to be, and the only force that could cause that would be friction, because it's the only thing that can possibly keep the coin on the record. So this is not a good vantage point to describe the forces on it, so I need a different vantage point. So I'm going to consider a possible different vantage point. Here's my different vantage point. I'm going to look at the disc from the side and also look at it when it's perfectly, perpendicular to us at that moment, because then I can probably identify all of the forces acting on the coin. mg downwards, normal force upwards, and friction to the side. finding the right vantage point in problems isn't always easy. And there are some troubling ones that we will have to deal with eventually, but we're going to leave those out for right now, like banked curves for cars and stuff like that. What kind of friction am I talking about here? So we're talking about the inequality, right? And when I look at my unbalanced forces here, I'm going to have net force in the x direction equals MAC. And net force in the y direction equals 0. So this problem is not that interesting once you get it laid out. I'm hoping you guys know what to do next. Looking around, I'm hoping probably something like friction equals m omega squared r. Switching over to the angular because an angular velocity was given. And probably something like normal equals weight. That all good? Is this too fast? It's pretty fast. But we've done this stuff before. Net force equals MA and net force equals 0. I'm feeling like some of this has got to become repetitive. Now, if we're trying to find a threshold, I think it's at this moment that you remember that we tend to sub into the inequality to come up with our threshold. Right now, we've done everything that Newton's laws will do. And Newton's laws has generated two relationships for us. They are unconnected because they don't have any shared variable except for mass. And I would never eliminate mass between two things. It never works out. But we do have this relationship. This would help us work in the coefficient. So if we're going to do something from this point, it's probably subbing into that relationship. So I'm thinking all of this here and all of this here. Is that what you're thinking? Or not thinking at all? One of those. So I'm thinking m omega squared r has to be less than or equal to US mg. This is why I would encourage you never to eliminate m between any two equations, because it often drops out. So if we had solved both of these for m and tried to put them together, what we would get probably wouldn't make any sense, because clearly the mass doesn't have anything to do with the answer. So I would encourage you never to eliminate m between two equations to join them together. You see what I'm saying? If not, make sure you work in all the important variables. That's why we had to use this. I'll cancel out the m's though. And now it depends on your question. Do you want to know what coefficient of friction you need to keep the coin on the table? Solve it for coefficient of friction. If you want to know the maximum speed that you can spin the record without the coin flying off, then solve it for the speed. I like to stay in variables because it gives you flexibility. There's clearly a coefficient of friction that I need to stay, greater than if I want to keep the coin on the table. Or there's a speed that I have to stay under if I want to keep the coin on the table. All right, so I think we've seen them all. Now, there's lots of other coefficient of friction. There's lots of other spinny problems, but you've seen the basics. So homework will drive home the rest. It's getting to the point where we have to start bringing up other stuff. So far, we have been really, really attached to these single body problems, which is what all of these have been. But there's a apparatus that we're eventually going to have to look at. for a centripetal motion lab. Basically, it's a don't hit your neighbor in the head lab, because that's what it is. I'm going to give all of you a short tube about the size of your hand, where you can pass a string through the tube and hang a mass here. Then you'll spin something light in a circle above your head. The goal is pretty simple: to levitate a mass here while you're spinning a smaller mass above your head. This lab has lots of nuance, but it's a combination of factors. And to understand how to do this lab, you have to understand the relationship between the forces on this object and the forces on this object. It should be not lost on you that if this object is merely hanging here, the net force on it will be 0. But it should also be clear that because this object is moving and going in a circle, the net force on it is going to be unbalanced. What brings them together? This magic string, where the tension provided by the weight that is hanging becomes the unbalanced force for the weight that is spinning. In order to do this lab, we are probably going to have to start talking about the multi-body problem. So to discuss the multi-body problem and to prepare us to be able to do this lab, we're going to have to introduce some new rules, because the multi-body problem hasn't been studied yet for us. We've been only studying the single-body problem. So there are a couple of new rules I want to introduce for the multi-body problem, and by new rules I mean just one, but it has dramatic implications. So that means a study of Newton's third law. You already have a colloquial expression for Newton's third law. For every action, there's an equal and opposite reaction. Heard it? That's not Newton's third law, but that is the colloquialism that tends to be associated with Newton's third law. Newton's third law is actually different than that. It's focused on force. So when we talk about Newton's third law, although the action-reaction phrasing isn't bad, it's not specific enough. So for what I want you to know, I'm going to phrase Newton's third law in 2 ways, and it represents the 2 ways in which I would like you to reference Newton's third law. And it does have other implications. The way it should be phrased is, for every force, there is an equal and opposite reactive force. Now, it states similar things to what I started off with, but it's focused on force. And it requires that we understand that it's equal and opposite. But I also want to state something else, and that is all forces. All forces come in action-reaction pairs. All of them. We don't always think about the action-reaction pair, but there is no force that is applied one place that is not also applied someplace else. Maybe the more obvious is to consider that for the whole semester so far, when we've talked about weight We've talked about it acting only on one person. But the truth is, there is a reactive pair here. And the reactive pair has always been and will continue to be the Earth. So although you experience mg downwards, the Earth experiences an equal force upwards. Now, there are important distinctions about these two forces. First, these two forces don't cancel out. They are internal to the Earth-person system, meaning they create a system between the Earth and the person. And therefore, these are an internal set of forces on the system. But the effectiveness of a force is dependent on what happens to one object, meaning the person experiences a variety of forces, and what happens to them is the result of all of them and their mass. This is also true for the Earth. The Earth is not just experiencing one force, it's experiencing lots of forces. What the Earth does depends on the forces that act on the Earth. What the person does depends on the forces that act on the person. The effectiveness of a force generally depends on the state of the object in which that force acts. Don't get the system confused with that. I can push the cart. I can push the cart across the room. But while I push the cart, I apply force to the cart. It applies an equal and opposite force back on me. I can't separate that. The moment I touch the cart, that's occurring. Because the moment I apply a normal force to the cart, it's applying a normal force to me. The pair of forces is created at that moment. The effectiveness of that force on the cart is greater than the effectiveness of that force on me. Probably because the cart has much less mass and is not experiencing a frictional force in the same way that I am. So that force is less effective at changing my motion, and it's more effective at changing the cart's motion. The effectiveness of a force depends on the object itself. These two forces don't cancel out, but they are internal to the cart-person system. Generally, what that allows me to do is give energy to the cart through this force. And the cart takes away energy using the force at the same time. You'll notice I gave energy to the cart moving it, and then something took the energy away. That was probably the cart ground system. I gave the cart motion, the ground took the motion away. Now, when we deal with Newton's third law, the importance of all of that discussion is to recognize that in any system, there are going to be internal forces. Forces that act within objects of a system. Understanding the parameters of the system can sometimes be challenging, but not impossible. As I push on the cart, I apply a normal force to the cart. The cart's probably experiencing a small frictional force. It's probably experiencing weight. It's probably experiencing a normal force. Whether or not the cart moves depends on the forces that act on the cart. Whether or not I move will depend on the forces that act on me. There's likely going to be my weight acting on the ground. Acting from the earth. There's likely to be a normal force that's balanced by that weight. There's going to be a force backwards on me from the cart. But there's probably also a frictional force forwards on me from the ground. That's what's keeping me from going backwards and maybe allowing me to accelerate forwards. When we look at all the forces that act in a system, there are internal forces in the system. These two forces are internal, and they're in opposite directions, but they act on separate objects within the system. Ultimately, there will be external forces that act on the system. They cause changes to the motion of the system. Me and the cart are a system, which is why there's an external force here. This is an external force, friction. It's external to the system. It allows the system to be pushed forwards. This frictional force is also external to the system, acts on the cart. So let's take a little look at this in practice. How much time do I have, though? It's 11:05. 3 minutes? That's enough time. So we'll deal with the simplest example of this that I can come up with. Let's go with a frictionless surface. Let's go with a 10 kilogram box and a 5 kilogram box. And you apply let's go with 30 Newton force. What is the force between the boxes? This is as simple of a third law problem as I can make. And this is a class of problems that I call train problems. A row of boxes or a row of train cars, they're very similar. The only difference is that boxes all experience normal forces, trains all experience tension forces, but they are the same problem. In the interest of time, though, let's identify the forces acting on each of the boxes. First box is experiencing 50 newtons of weight and an equivalent amount of normal force. It's also experiencing a 30 Newton force to the right. However, I have a surface in contact here, which must be causing a second normal force. And that normal force has to be this way, perpendicular to the surfaces in contact, which I'll name normal force B from the box. Question about that? All right. Second box gets its own set of forces. So 100 newtons downwards, normal force upwards. I'm not touching the box, so that 30 newtons doesn't act on the box. But there is a normal force that acts again here. It must be perpendicular to the surfaces in contact, which means it's this way. And this represents my third law reactive force. This force and this force must be equal but opposite. They connect the two objects together. This is how I'm able to push the other box, by pushing through the first box. And these problems are not challenging once you understand this. The net force in this box is going to equal MA. In the x direction is the only place I have to worry about this because they're balanced up and down. So that's going to be normal equals 10A. The first box is experiencing two horizontal forces. So 30 minus normal equals 5A. And now I've done it. I've done all of these steps all the way to the bottom, and I've got two expressions. Do you notice that it's two expressions with similar unknowns? Do I have to prove to you that the accelerations here are likely the same? That it'd be difficult for box 1 to accelerate faster than box 2 without going through box 2? And if box 2 is accelerating faster, it would separate from box 1. So does it make reasonable sense that these are the same accelerations? So I'm just going to do quick substitution. This will tell me the force between the boxes. It's almost always easier to find the acceleration first. And what I get is an important outcome. 30 minus 10a equals 5a. We've eliminated the internal force between the two boxes and come up with a new relationship that combines the two boxes together. Do you notice that if I bring the accelerations to the other side, that I get something that appears to be Newton's law? Do you see that this is the sum of the masses? I see that? You'll know you've done one of these right if at the end of your problem, you see masses added together. That's how you know you've done these problems correctly. I guess that's all we can do. And that was a lot. That was a lot. Actually doing to try and talk to you about the difference between angular motion and linear motion. And although I did talk about this yesterday briefly, I want to be very clear about some symbology that's here. We use the Greek letter omega for angular velocity. And I'm not sure I said that in this class yesterday, so I want to make sure I get it in all the classes. It looks like a W with a little extra flair at the end. It's a lowercase letter omega, and it stands for angular speed or angular velocity. Now, we could also use rotational speed or velocity. Generally, angular speed or rotational speed is given in either rotations or radians per time. So minutes, seconds, something like that. It doesn't make sense to talk about how fast the person's going in referencing a ride that spins. It makes more sense to reference the spin rate of the ride. Now, the person being on the ride has a linear velocity. Now, I need to say this, and I hate saying it because I think it's something that you should know, but I know that that doesn't happen. Even for me, I needed my face rubbed in this too. The person's linear velocity is tangent to the circle, always. So no matter where they are, their velocity will be tangent to the circle. Right? Linear velocity, tangent to the circle. Now, I think all of you probably can imagine that their linear velocity has something to do with not just how fast the ride is spinning, but where they're located on the ride. If this is the center, doesn't this person make a smaller circle in the same amount of time that this person makes a bigger circle? So their linear speed probably has something to do with the radius. In fact, if they were at the center, would they have a linear speed? No, they'd just be going in a circle. So linear speed is related to radius. But the entire ride has only one rotational speed. There's lots of linear speeds on the ride, but the ride itself has one rotational speed. Everybody okay with that? Now, there is a way to convert from linear speed to angular speed. And you already know what it is. It's the definition of circumference. Linear equals angular times radius. That's the conversion. So linear equals angular times radius. It's true if we talk about linear speed. It's true if we talk about linear displacement. All of these are the same conversion. The linear displacement is a circumference when you go 2 pi radians times a radius. That's where the definition of circumference comes from. So it is important to understand that this is a conversion for a linear speed from an angular speed and vice versa. But if you are taking notes to this point and you would like to make sure you get this right, this will have to be in radians. Have to be in radians. Unfortunately, I said the ride rotated 1 rotation every 6 seconds. This is an angular speed, but it's not in radians per second. So if you need it in radians, you have to know how to do a conversion. I'm of a mind that I probably should show you how to do a conversion, just in case. So if you know how to do this, great. If you don't, I'm speaking to you. I'm giving you what you need, so you can't say we never did that before. I'm a unit multiplier kind of person, so I always make the fraction, always. That way I never have to say, oh, I divided when I should have multiplied. I hate that. I hate hearing it too. It just means that you are just in a hurry. I want to be left with radians, and I have rotations, so I have to put rotations on the opposite side of the fraction. And then I need to know my conversion fact, and it's every 1 rotation is 2 pi radians. So it looks like I multiply here. Okay, as an aside goes, that's a lot. But I also believe that it's not so terribly difficult that I can't use this from now on. If I'm wrong, please speak now, and we'll do some more review before I move on, or just assume you can do it. Alrighty, feeling good about that now. So